Well, welcome everybody to this very intimate colloquium, because there is another cosmic show going on that drove people away from Tucson. And today it's a pleasure to have Trevor Dorn-Wallenstein here. Trevor did his PhD at the University of Washington and is now a postdoctoral fellow at Carnegie, Pasadena. And Trevor is an expert on massive stars, and in particular evolved massive stars, the one close to the explosions. And I'm sure today he's going to tell us more about his work across observations, data analysis, and theory of these objects. And
yeah, awesome. Can everybody hear me? Awesome. Cool. I like to be heard. All right. So thank you all for joining me here on Eclipse Day. I'm really excited to be here. Has anybody heard from your colleagues on the path of totality? Did people get to see it? Awesome. Cool. I was going to say, if they didn't, we could make them super jealous with this awesome talk. We still will. So something you should know about me is that I am really easily distracted. I just have zero attention span, which means that I work on a whole bunch of different things, which makes it kind of hard to put together a cohesive talk about one thing. So rather than do that, I wanted to give you all kind of a broad overview of the things that I'm thinking about in massive star land, to maybe spark some interesting discussion and talk about all the cool stuff. Of course, I still need to have a talk title, and so my talk title is More Pixels, More Stars, More Physics. What I mean by that is that we're in this really exciting time to study evolved massive stars in particular. We have really large sample sizes that we've not had access to historically, enabling us to do some really interesting physics. And so let's get into it. Assuming that this works. This is not working. Uh-oh, we tested this and it totally worked. Now it's not. Let's see. If I do this. There we go. Okay. So are there students in the room? Awesome. I want to bring you all with me. And so I'm going to get started here, kind of grounding us in the HR diagram, because I like to think in terms of the Hertzsprung-Russell diagram, luminosity on the y-axis and temperature on the x-axis. I don't care about any of it. When it comes to massive stars, these are objects with initial masses greater than about 8 or so solar masses. They're up here at the top of the HR diagram.
okay.
We're back. Okay. They're up here at the top of the HR diagram, and we observe them in this really spectacular variety of evolutionary states. From O and B type stars on the main sequence, as they evolve across the HR diagram to become yellow and red supergiants, and even more exotic phases like Wolf-Rayet stars, luminous variables, all kinds of weird and funky things that are lots of fun. Unfortunately, though, they're hard to form. If I show an initial mass function, right, the probability of forming a star as a function of its initial mass, generally it's easier to form lower mass things than it is to form higher mass things. But as a baseball fan, I like to ground us in some hard numbers. So before the baseball season began, I dug up the odds for each team in the National League West to make the playoffs. And so if the Dodgers and our beloved Arizona Diamondbacks are like the probability of forming a 1 solar mass star, the probability of forming a 10 solar mass star is like the Colorado Rockies making the playoffs. And if you're not a baseball fan, that joke is hilarious, trust me. So not only are they hard to form, massive stars also have incredibly short lifetimes. Here's the rough kind of scaling of how a massive star's main sequence lifetime scales, or how any star's main sequence lifetime scales with initial mass. It is a strong power law of initial mass. Generally, we're talking about things that are only around for 10 mega years or even less. And so these things are rare. They don't stick around for long. So why should you care about them? I think they're really interesting. You know, there's at least a few people here in the room with me who think they're interesting as well, for a lot of different reasons, right? They are sources of feedback through their kinetic energy injected via their winds, radiative energy injected via their strong ultraviolet flux, at least when they're on the hot end of the HR diagram. There's an immense amount of energy injected into their surroundings. There's also an immense amount of stuff injected into their surroundings through mass loss, through stellar winds, polluting the interstellar medium with lots of really interesting things that we like to talk about. They also explode. Well, mostly, we think they explode. Sometimes they don't, and it gets kind of confusing. But at the ends of their lives, massive stars experience core collapse, injecting lots more energy into the interstellar medium, lots of interesting chemicals. They do interesting things. Massive stars are awesome. Speaking of those interesting things, I'm showing here a periodic table of the elements where each element is colored by the kind of astrophysical process that is responsible for forming that element. And even though massive stars are highlighted here in green, a lot of these processes happen here in massive stars. And so if you care about the carbon in your bones, or the gold in your fillings, or the technetium in your phones, you should care about massive stars because those elements were formed in a massive star. Of course, we're in this really exciting time as well for compact object mergers. And if you care about the neutron stars and black holes that we're observing merge with gravitational radiation, well, then you should care about their massive star progenitors to understand the populations of stars that are going to be merging, the populations of compact objects that are going to be merging. And of course, massive stars are responsible for lots of general shenanigans, right? They do weird things. They have outbursts, they burp, they jiggle, they do all kinds of wild things, and that makes them really fun to study. But there are a lot of open questions when it comes to massive stars, and I'm highlighting just a few of them up here. Things like, what role does rotation or maybe binary interactions play in the evolution of massive stars? What are the mass loss rates of massive stars? That turns out to be a really tricky question to answer. How does that mass loss affect massive star evolution? What role do eruptions play in the evolution of the most massive stars? Which stars actually do explode? I mentioned that that's a complicated question. I'll get to it later in the talk, but it turns out to be a really cool one. And finally, it's a little inside baseball, but I think it's one of the most important kind of theoretical things that we need to understand about the evolution of massive stars, which is, how does the material that is synthesized in their cores get mixed throughout the core? How does it make its way out into the envelope? How does it affect the structure of a massive star? How does convection actually work? What about convective overshoot? There's all kinds of really neat physical processes that we really need to understand massive star evolution. So that's massive stars in general. Why should you care about evolved massive stars? The things that are in their last 10% or so of their lifetimes after they've left the main sequence. This question was kind of phrased a slightly different way by Kippenhahn and Weigert in their 1990 textbook, where they said that evolved massive stars are this like magnifying glass, relentlessly revealing the faults of calculations of earlier phases. What they were referring to here is the fact that if you take observations of, say, an O and B main sequence star and confront them with our theoretical models, well, we could do a pretty good job, right? Observations in theory, they played along pretty well. But the tiny little gaps in our understanding of the theory, when you take them and propagate them forwards in time to evolve massive stars, mean that the observations in the theory start to disagree. I like to kind of turn this phrase around. I say that if you have a magnifying glass, you should use it. If our uncertainties in theory are blown up when it comes to the evolved massive stars, then we should use evolved massive stars as a precision probe of these physical processes. That sounds easy. It's easier said than done. Of course, our magnifying glass is foggy. That fogginess in our magnifying glass comes from two things, really three things. So observationally speaking, like I said, massive stars are hard to form. They don't stick around for a long time. And so our sample sizes are absolutely tiny. We just don't have the statistical lever arm to place constraints on the physics that we care about. And theoretically, we have this problem, right? This is kind of an illustration of what Kippenhahn and Weigert were talking about, where you have these tiny little variations in the input physics for our theoretical models of massive star evolution. And I'm showing that here in the HR diagram. This is a stellar evolution track, or 6 stellar evolution tracks for a 20 solar mass star computed by 6 different evolutionary codes, all of which have perfectly reasonable assumptions for the input physics. And while they generally agree along the main sequence, after these models leave the main sequence, all bets are off, right? The luminosity of this track after the main sequence varies by 0.2 dex. Whether or not this model does a loop or not, right? We don't really have a good constraint, an agreed upon evolutionary scenario for this 20 solar mass model. Now, of course, y'all invited me out here, which means that I get to kind of stand on a soapbox and talk about another problem that I don't think we talk about often enough, and it's a statistical problem called the null space. So the plot that I just showed earlier shows how pretend these are 2 sets of kind of physical inputs for our model. And even though these sets of physical inputs are very close together, When we project them into an observational space, we get results that are very far apart. The null space is the exact opposite. I can have a whole bunch of very different physical inputs, and yet when I project them into the observed space, they predict almost the exact same thing. And so not only do our models yield a wide variety of predictions, but even if we have reliable observations, the set of models that actually fits those observations is too big. And so that's kind of another thing clouding our magnifying glass. Of course, it's not all hopeless. I wouldn't be here giving this talk if it was. We're in a really exciting time to study massive stars observationally. Right? We have these really exciting spaceborne missions like Gaia, TESS, JWST that are currently flying, and hopefully soon Roman will be flying, giving us some really, really exciting observations. Not only that, there are probably a few people in this room who are excited about GMT and other upcoming ground-based facilities. The stat that I like to quote is that with GMT, we can get a spectrum of an individual massive star out to 50 megaparsecs, something like that, which is just wild. And so we have a really exciting ability to get follow-up from the ground. Couple that with advances in theory that we're already making, and we can take some of the techniques, some of the power that's already been developed for low mass stars, where our ability to have large sample sizes and well understood theory have already been well matched with each other. And we can take those ideas, those techniques, apply them to study evolved massive stars and make some get a lot of really cool insight. So hence the title of my talk. We have more stars thanks to missions like Gaia. We have more pixels, where when I say pixels, I just kind of mean resolving power, whether it's spatial or spectral or Fourier. We have a lot more pixels per star. And we can use these two things to tell us about stars. So I'm going to divide this talk into kind of two sections. One is more stars, and the next is more pixels. So I'm going to take you all back to my very early days as a graduate student. These are kind of like, these are old enough studies that I don't want to spend a lot of time on them, but they're important for the story I'm telling. So I'm going to get through them pretty quick. In 2018 or so, I was really interested in binaries. It turns out that at least 70%, if not 100% of massive stars are born into binary systems. And a good chunk of those systems are going to interact. They're going to exchange mass over time. And so I was really curious, what fraction of massive stars are actually in binary systems? And does that number, the binary fraction, change with environment? Does it change with the metallicity of the host galaxy? So there's a lot of ways to answer this question. One of the most direct ways is to go take a 10-year-long radial velocity survey of as many stars as you possibly can to determine which of them are in binary systems, and then do some really tricky statistics to back out the actual intrinsic binary fraction, which is really hard to do and takes a lot of time. Instead, you can just look at populations of stars, and you can look at the impact of binary interactions on populations of stars. So what I'm showing here is output from the binary population and spectral synthesis code, or BPAS, which is absolutely wonderful code that everybody should use, or a wonderful set of evolutionary models that everyone should use. And I'm showing the number of stars on the y-axis as a function of time since a single age stellar population was formed. And I'm showing that for two different kinds of evolved massive stars. One is the Wolf-Rayets, which I'm showing in purple here. These come from fairly massive progenitors of about 40 solar masses-ish and up. So we see them at fairly early times because they evolved the fastest. There's not a lot of them because of the IMF, right? Those really massive stars are down-weighted. And then kind of in a window that begins to overlap with the Wolf-Rayet stars, but really doesn't start to show up till tens or hundreds of mega years after the population forms, we see a big chunk of red supergiants showing up. These are kind of the massive counterparts of red giant stars, if you're familiar. A lot more of them, again, thanks to the initial mass function, right? We're looking at slightly lower mass progenitors. These are weighted higher in the population. Now, this is what I get for a population of 100% single stars. If I instead show a population of 100% binary stars, we see some really interesting things. We see that in close binary systems, the primary stars that would become red supergiants instead exchange mass with a companion. Their envelopes get stripped, And instead they become, well, I'm going to put an asterisk on this, but stripped envelope Wolf-Rayet stars. And so right at late times, we see a big peak of Wolf-Rayet stars and the word has dropped out of my head, simultaneous decrease in the number of red supergiants. And of course, that asterisk is the fact that these low mass strip stars are probably not going to look like classical Wolf-Rayet stars with these big whopping emission lines in their spectra. And I'm showing some work from, until recently, Carnegie postdoc Ilva Goldberg, who looked at, or actually did the spectral synthesis and showed that you can actually go look for these things, but you have to be really careful with how you do it. In addition to thinking about binaries, I was also interested in comparing these results with some predictions from stellar evolution models that incorporated rotation. And so I constructed a whole bunch of synthetic stellar populations. I projected these populations into this observed space of two different ratios of the relative number counts of different types of evolved massive star. This is kind of like a classical BPT diagram, except you're just counting stars and plopping them up here. And what we found is that in the center panel, you need populations that include binary stellar evolution in order to explain observed number counts of massive stars in the Magellanic Clouds. Not only that, but we actually took this method and we applied it to a whole bunch of different populations all around the local group. And that's what I'm showing here, where I'm showing the red supergiant to Wolf-Rayet number ratio as a function of metallicity for a whole bunch of different synthetic stellar populations. So this method works. You can do some really interesting science with it. You can get some really cool answers. But the thing is, this project here required doing an incredibly careful amount of work on hundreds of stars, going after these stars spectroscopically in order to confirm their membership in their host galaxies, confirm their status as Wolf-Rayet stars or red supergiants. That's just a lot of work. Not only that, but each and every single host galaxy in that population required a boutique method to separate out the genuine massive stars in that galaxy from the stars in the foreground from our own galaxy. So that's hard, that's bad. And so right around this time, I found myself saying, I wish we could somehow get larger, more complete samples of massive stars that were homogeneously selected. And it'd be awesome as well if we could also get like temperatures and luminosities and classifications and all that really interesting stuff, to which Gaia Data Release 2 said, hello. Gaia has truly been a revolutionary point in our studies of evolved massive stars. With Gaia's astrometry, which we can use to measure really careful.
Sorry.
We can use Gaia to get some really careful measurements of stellar luminosities and actually construct color magnitude diagrams that we can trust and combine this with our understanding of where massive stars live in the CMP, identify a sample of 6,500 highly likely evolved massive stars in the galaxy and the Magellanic Clouds. Of course, actually classifying these stars is still a problem, right? We can have all the stars that we want, but we need to determine which of these things are Wolf-Rayets and red supergiants, which of them are on the main sequence, which of them aren't. So of course, classification is a task that we can assign to a machine learning kind of thing. But I want to be very clear here. Machine learning is not magic. Frequently, it's seen as this kind of black box where we can put all of our problems and get answers out. And it really isn't. It does require careful work. But I also kind of want to demystify it a little bit. All machine learning is this, or all machine learning is this. We start with a sample of objects, say 6,500 evolved massive stars. For each of these objects, we assemble what I'm going to call features as input for our machine learning thinking. That can be photometry, it can be astrometry or spectroscopy, it could be variability metrics that we collect from a light curve, it can really be anything that you want. We then run these features through a function. This function would be nice if it was a linear function with well understood properties, and that function predicts a label as an output. And that label can be a classification like red supergiant or Wolf-Rayet star. It can also be a continuous quantity like effective temperature or luminosity, in which case this task is called regression. And so generally there are two big types of what's called supervised machine learning, classification and regression. If this is getting to be a little bit too jargon heavy, pretend like I've collected a whole bunch of features that I'm going to call X and I've created a magical function that predicts my labels y as a function of x, such that if I get a new object, all I have to do is measure its x, run it through my function, and I get my y. Okay, so let's talk about how we did this for our sample of 6,500 stars. For our features, we wanted to come up with a feature set that would mimic something that we were going to have in the near future and which we are already getting, which is near and mid-infrared photometry. So we wanted a feature set that would mimic photometry from JWST as well as from Roman, which is really nicely covered actually by the WISE and 2MASS surveys. And so we collected photometry running from J-band as well as the Gaia broadband photometry, so kind of red optical, all the way out to WISE W4, which is I think at 24 microns. I forget the exact number. So with our features in hand, we can now come up with our labels that we want to predict, and we need a sample of labels that we can trust, a ground truth to compare our predictions with. And if you want a whole bunch of labels for a whole bunch of stars, the place to turn is Simbad, but it turns out that labels in Simbad get messy. We had to come up with this really horrible flow chart to take the spectral types that you download from Simbad and turn them into meaningful class labels like luminous blue variable or red supergiant. And it turns out that when you try to do machine learning with this, it doesn't work. Trust me, I tried really hard to make it work. It didn't work. But if we bin these labels into 4 coarse categories: hot stars, that's O, B, and A stars of any surface gravity; cool stars, that's yellow and red supergiants; contaminant stars, this is lower mass red giant and AGB stars that frequently contaminate our samples of evolved massive stars, as well as emission line objects. These are the luminous blue variables, Wolf A stars, B bracket E supergiants, rare phases of stellar evolution that we can use to constrain our models of stellar evolution. So that's our 4th class here. And it turns out that you actually can do machine learning with this. You can actually get really reliable results. Before I move on, I'll point out this class here at the bottom, this unknown label. There are about 2,500 stars in our sample that actually just had no spectral type on Simbad. They're just stars. And so at the end of the day, we're going to take our classifier and use it to provide labels or spectral types for these stars for the very first time, which is very exciting. Okay, so what can we actually do to do this classification? The tempting thing is to construct a neural network and run the neural network, but I'll be honest, I don't understand neural networks, and I don't think a lot of people understand them particularly well, especially what's actually going on underneath the hood. I would rather use an easy to interpret model, something that's linear, like a support vector machine, which is a fancy word for drawing a line. So I have this imaginary feature space here where I have my blue stars down here in the bottom left, and my red stars up here in the top right. The support vector machine simply finds the line that maximizes the distance between that line and the closest member of each individual class, right? Just maximize these 2 distances here, which is great. Of course, I've constructed this toy example to have a star that gets misclassified. One of the other benefits of a support vector machine is that it allows for misclassification, which is nice. And not only that, but because the whole math of a support vector machine is based off of distances, we can play a cool mathematical trick. I know there's a lot of theorists here, and y'all like to do math, apparently. So what we do is redefine how distances work in our feature space. By doing that, what we are doing is implicitly projecting our n-dimensional feature space into an infinitely dimensioned feature space. We draw a hyperplane in that feature space, project it back down into the actual space of observed features, and it looks like a curve. We're not actually doing that, right? I don't have code that can make an infinitely dimensioned feature space, but it's equivalent mathematically, which is pretty cool. So we take our support vector machine, we train it on a training sample, we then apply it to a test sample that's been withheld from the model up to this point, and we ask, how well did we do? How well did our predictions for a given class actually grab all the members of that class? That's the completeness here on the x-axis. We want high completeness. And how, of the stars that we say are a given type of star, what fraction of those stars aren't actually that type of star? How contaminated is our sample? That's what I'm showing on the y-axis. Now, for the hot stars, cool stars, and contaminants, we do really well. This is not surprising. Like separating out hot stars from cool stars is a pretty simple thing in color space. But more surprisingly, we do incredibly well at identifying emission line stars based off of only broadband infrared photometry, right? We don't actually have any narrowband filters. There's nothing that would necessarily be a smoking gun that these stars are emission line objects, but we still do a pretty good job identifying them, which is nice. Not only that, I'm showing y'all here all of the list of features that actually went into this classifier. You don't need to know what all of them mean. All you need to know is that you only need these first 4 to get maximum performance out of your classifier. If you want to read through them, you can, but the big takeaway is that you don't actually need photometry redder than 4.6 microns. So if you're doing stellar population studies with JWST data, you don't need to go that far out into the mid-IR, which is pretty exciting. You also don't need variability. I didn't really get a chance to talk about this, but WISE data actually comes with variability, or rather with sparsely sampled light curves from which we extracted variability metrics. You don't need them to do a good job. So this method is pretty robust and applicable, which is great. Okay, let's go back to those 2,500 stars that I mentioned earlier that didn't have a label. They now have a label, or at least a coarse label, right? We've predicted which ones are hot, cool, contaminant, and emission line stars, of which there's 14 of them were predicted to be emission line stars. Of course, our contamination is 0, so we expect of these 3 or 4 of them are likely contaminants. And I want to highlight a student of mine, Sean Catino, whose research note, looking at all of the stars in this sample visible from the northern hemisphere, was just accepted. We did find a new emission line star here, which is really exciting. Empirically, we are consistent. 1 out of 2 stars that they studied was an emission line star, which is consistent within Poisson noise with this 14, which is really exciting. Okay, so shortly after publishing this paper in 2021, I said the following. Wow, as fun as that was, wouldn't it be awesome if I could get more than just the 4 spectra that my students studied, right? Doesn't even need to be high resolution. It could be low resolution. And, you know, what if those spectra were also presented as this like really nice linearized basis set of spectra as well? If you can't tell where I'm going, Gaia DR3 said hi. So with the 3rd data release of Gaia came a whole bunch of low resolution spectra for every single star in Gaia brighter than a magnitude of 17.65. These spectra are really neat, even though they're only about a resolution of 50. They're presented as a series of coefficients. So rather than just downloading wavelength and flux tables for each star, you are given a set of 110 coefficients that can be used to reconstruct the spectra. Those coefficients are constructed by fitting the actual spectra with a series of basis functions. These basis functions are linearly independent. In other words, each coefficient contains a different bit of information about each spectrum. That makes them perfect for doing machine learning, right? We love linearly independent features. And so we decided to do some machine learning to actually derive temperatures and luminosities for a whole bunch of stars in our sample. So to do this, we had a bit more of a tailored sample. We got about 640 cool supergiants, so yellow and red supergiants, the Large Magellanic Cloud, using Catherine Nugent's work from 2012 to get us photometrically derived temperatures and luminosities. And just to kind of illustrate that these temperatures are reliable, I've shown the sampled spectra here, wavelength and flux, and we can see that the cool stars indeed look like cool stars, the hot stars look like hot stars, and the schnozberries taste like schnozberries. And again, just to highlight how awesome Gaia is, it becomes trivial to just take our stars, look at parallax and proper motion, and toss out the stars that are in the foreground, right? These become very obviously separated from the Large Magellanic stars here in the bottom left. It's very easy. As an observer, this is amazing. Okay, so we wanted to take our features, our 110 spectral coefficients that we've normalized out to put them all in the same dynamic range, as well as our broadband photometry, the Gaia G, as well as B and R, and extinction measurements that we take from a dust map of the Large Magellanic Cloud. And we try to see if we can take these features and regress, fit a function that predicts effective temperature, and luminosity. We tested a whole, I think all told, we tested 11 different types of regression, all the way from simple linear regression up through a neural network, just to demonstrate that even though none of us knew how neural networks worked, we could still get one working. It's very easy to get into a lot of trouble with neural networks. At the end of the day, though, the best performing regressor was a Bayesian ridge regressor, which is just linear regression, but with another term added to keep the model from getting too complex and from overfitting the data. We tested a whole bunch of different combinations of features. We found out that if you want to do well, you really do need the spectral coefficients. You can do nowhere near as well as just using the broadband photometry doesn't get you anywhere near the performance of the spectral coefficients. So you need spectra. And you don't even need all 110 coefficients. You can do it with only about 10 to 20, which is nice. And so we took our regressor and we applied it to a much larger sample of about 5,000 cool supergiants from Ming Yang's work in the Large Magellanic Cloud to derive this incredibly well-populated Hertz-von-Russell diagram. Right, this is essentially every single cool supergiant in the LMC right here, which is very exciting. Of course, we did some validation work, right? So we looked at our effective temperatures to make sure that stars with later spectral types indeed were cooler, which they are. You shouldn't use this to actually do effective temperature, rather temperature scale work, because there's a lot of scatter in our results for various reasons. But generally, we compare very well with literature effective temperature scales for cool supergiants in these environments. So why did we go through that exercise, right? Was it just to kind of do machine learning because we could? Turns out you do really need it. So I'll start here on this right-hand plot where I'm showing effective temperature as a function of J minus K, right? A near-infrared color that's often used to derive effective temperatures of cool supergiants. So you'll notice a couple things. One is that this relationship goes vertical. Right? This is because after a certain temperature, right, your flux has moved enough into the blue that by the time you're at J and K, you're in the Rayleigh-Jeans tail. 2-mass filters are, I think, Vega mags, and so by definition, you're at a color of 0. Not only that, but these hotter stars also, because they are bluer, the near-infrared flux, the uncertainties are larger, and so that uncertainty kind of scatters you around horizontally in this plot. And because this relationship goes vertical, a little bit of scatter results in a large amount of uncertainty in effective temperature. And so if you care about stars in the warmer part of this region, essentially anything above a log temperature of 3.7, which is what, 8,000 Kelvin and above. If you care about these stars, then you should care about the optical, you should use Gaia, and you should use this simple regressor to derive their temperatures. This plot, there's a lot going on in here, but the big takeaway, though, is that these stars that are up here, these red supergiants, because most of their flux is in the near infrared, if you are too faint to be observed by Gaia, you can still be observed by 2-mass. On the other hand, for everything below this line here, so effectively every single red supergiant, if you are just faint enough to be observed by Gaia, you are not detectable by 2-mass. In other words, for a yellow supergiant in M31, that's bright enough to be observed by Gaia, and so you can use this method to get an effective temperature, but it's not bright enough to get a photometric temperature from 2-mass, if that makes sense. Okay, so let's do some astrophysics now with this sample, right? We have this incredibly well-populated HR diagram. Let's see what we can find hidden in here. This top left panel here shows an HR diagram now filled with kind of a smooth 2-dimensional histogram of the HR diagram. It's called a kernel density estimate. They're really cool. And it's dominated by the lower luminosity red supergiants. This is not surprising because in this part of the HR diagram, the red supergiant phase is the longest lived. And so our population is dominated by the lower luminosity ones, which are more common thanks to the initial mass function. However, if we take each row in this image in the top left and divide it by the overall luminosity function of the data, we get this plot on the top right, which is essentially showing the typical lifetime or the population of this Hertz-von-Russell diagram as a function of temperature but with the luminosity function taken out. So we can see again, this plot is dominated by the red supergiants because the red supergiant phase is the longest lived. But there is this kind of spray of stars up here in the yellow supergiant regime up at the highest luminosities. Similarly, this bottom left plot, if we take each column in this image and normalize it by the distribution of temperatures in our sample, you get this, which is essentially a luminosity function as a function of temperature. Our luminosity function is dominated by the lowest luminosity stars in our sample. That makes sense. But again, in the yellow supergiant region, we notice this flattening of the luminosity function. If I combine these two panels into this panel on the bottom right, and I'm going to slightly change the color bar to emphasize a couple things. I'm not cheating, I promise. I'm just changing the color bar to be symmetrical. We see this flattening of the yellow supergiant luminosity function, or you can think of it as an extension of the yellow supergiant lifetimes in this region of the HR diagram, accompanied by a corresponding decrease, a steepening of the red supergiant lifetime here. So there's some really interesting stuff encoded in this plot. I'll talk about what I think it means, how I interpret this in a little bit, but we need to fold in the next section of the talk. So I'll pause here. Are there any questions about what I've talked about thus far? See,
oh, yeah, I have one.
Yeah.
How do you have to deal with BE stars, or they're so rare that you don't worry about them as components?
In this population?
Well, not in this,
Yeah.
This was a question more on the earlier stuff,
Oh.
on the classifier.
Yeah, so those are lumped in with the emission line objects.
Okay.
In fact, my student's research note was a new BE star that they found. So yeah, it would be great if we could separate out BE stars from Wolf-Rayet stars, right? They're going to look different in broadband photometry. We kind of have to lump them together. So that's something I'd like to think about in the future.
Thank you.
All right,
Cool. So that was the more stars section. Let's talk about more pixels.
actually, I have a question.
Yes.
You were talking about using the reddening from the
Yeah.
extinction maps. How did you actually know extinction to each star? Because they could be anywhere along the line of sight.
Yeah, good question. So we looked into not just using, right, like the pixels in the extinction map are fairly large, right? So not only do you have line of sight effects, but you also have, variability in each pixel from star to star. So we also looked at, we used spectral types as well as observed colors to estimate an EV minus V. And you actually wind up doing even worse with that, mostly because there's only, from our training set of 640 stars, only 200 of them had spectral types. So, you have kind of a trade-off of better extinctions, but smaller sample. That said, the information that you need to get around extinction is still contained in the spectral coefficients. Right? I couldn't point to, the second coefficient gives you extinction, but all that information is still contained in the spectrum. And so our model captures it pretty well. Yeah. Cool. Okay, so more pixels. Like I said, I mean here not just spatial pixels. I also mean spectral resolution or Fourier resolution. We're in this really exciting time where we're getting a lot more of that for massive stars. So yes, that's the asterisk to tell me to talk about what I just talked about. So right around the time when I was saying this earlier, in addition to Gaia DR3 saying hi, the Transiting Exoplanet Survey Satellite also said hi. Now, if you're unfamiliar with TESS, TESS is a planet hunting mission. It stares at a whole bunch of stars and looks for planet transits. But it turns out that if you stare at stars and look for transits, and some of those stars are massive stars that aren't going to have planets anyway, you learn a lot about the massive stars. Now, prior to TESS, systematic studies of high frequency variability in evolved massive stars were more or less non-existent. Right? We had Kepler, but Kepler was a pencil beam looking at the same patch of sky, and there were something like 7 B stars. That was the closest to a massive star that Kepler got. I think one of them was a B4. That was the earliest spectral type star that Kepler looked at. But TESS has all sky coverage, which means that we now get 2-minute cadence data of dozens or hundreds of evolved massive stars. So we can actually start to take the lessons that we've learned from missions like Kepler and apply them to study evolved massive stars. So we did that in 2019. We looked at a grand total of 8 stars that were observed in test sectors 1 and 2, and we found that they were variable, which was really exciting. But before I talk about what exactly was varying, I want to talk about 2 little pieces of physics. They come from opposite ends of the HR diagram, but I promise it's going to make sense when I bring them together. The first is stochastic low frequency variability. So it turns out that when you look at sun-like stars and like Kepler-like curves of sun-like stars, we see this stochastic flickering that comes from convection. It comes from granulation in the surface of sun-like stars that manifests itself as this low amplitude stochastic wiggling in their light curves. But this is actually a light curve of an O star from TESS. And so it was kind of confusing, right? This result, stochastic low frequency variability, was first detected in 2011. And it was a little bit surprising because massive stars have, or O and B type stars, have radiative envelopes. They shouldn't be, there shouldn't be granulation in them. And so there's 2 ideas for what could be producing this stochastic low frequency variability, this kind of rising power at low frequencies that we see in periodograms of these light curves. One is an idea called internal gravity waves. You essentially have the convective cores of these O and B type stars, right? They kind of perturb the inner layers of the radiative envelopes of these stars. Those perturbations travel out through the envelope as waves, where we observe them at the surface, potentially as stochastic low frequency variability. The other idea says that, okay, no, what's, the transport of these waves through the envelope, we don't necessarily think that might look like stochastic low frequency variability. What if it still is convection? What if, and we know this exists, that a few pressure scale heights beneath the surface of these stars, there is an increase in the opacity due to iron peak elements. And so if in this iron convective zone, there's subsurface convection, and that subsurface convection could drive the motions at the surface that we observe as stochastic low frequency variability. So 2 possible theories, 2 ideas for what could be driving this. Now, at the exact opposite end of the HR diagram, we have a really interesting problem called the red supergiant problem. And I promise there's a reason why I'm skipping around with this. So our standard model of stellar evolution predicts that an O and B star is going to evolve across the HR diagram to become a red supergiant. It's going to explode as a type 2p supernovae. And we think that this picture applies for 8 to 25-ish solar mass stars. It's really hard to measure the initial masses of stars. I like to think in luminosities, which we can sort of measure reliably. That's all stars below a luminosity of 5.5 when we observe them as red supergiants. However, when we look at populations of red supergiants, or when we get pre-explosion imaging of red supergiants, we find that these lower luminosity ones are exploding, but at a log luminosity of about 5, we actually stop seeing them explode. And so this discrepancy between we think that 5.5 and below should explode, but it turns out 5 and below explode, has been dubbed the red supergiant problem. Don't just take my cute little animations word for it, though. There's a long history of literature looking at this missing progenitor problem. There's a few proposed solutions. One is that maybe these stars actually aren't blowing up at all. Maybe instead, these massive 20 to 25 solar mass red supergiants are actually directly collapsing. There's a whole bunch of different theoretical work showing these kind of islands of implodability, where there are these initial mass windows where rather than exploding, they actually implode. And this window kind of moves going from 1D models to 2D to 3D. The predictions kind of change around. This is a really exciting and intriguing option. Another is just statistics, right? The initial mass function is a thing. What if we observe for longer? If we observe for longer, maybe we'll see these higher mass progenitors. But at this point, the evidence is clear. The significance of the red supergiant problem is something like 5 sigma. So this really is a thing. Another possibility, and that's the one that I really like, is that rather than exploding as red supergiants, what if these stars are actually losing their envelopes somehow either through winds or outbursts, interactions with a binary companion. And after they lose their envelopes, they evolve across the HR diagram to become yellow or blue supergiants before exploding or imploding. That raises the problem, though. If we want to prove that that solution correct, we need to actually find post-red supergiants. There's a few ways of doing that. We can try to look for stars like this. This is the Runny Egg Nebula. I love that. It's a yellow supergiant that has this big cocoon of its envelope that it had previously ejected. But that's tricky, right? The star needs to be close enough, and the circumstellar material needs to be bright enough that you can detect it. You can also look in a star's SED out in the infrared and try to find evidence of this circumstellar material, but that's not necessarily a smoking gun, right? Could be mass loss in the pre-red supergiant phase. It's also, excuse me, you're not also guaranteed to detect this if there's material there. You could even go and look for the peculiar abundances that you might expect at the surface of a star, of an evolved massive star whose envelope has been stripped. I instead decided to go about this the hard way and look for pulsations. So this is a kind of complicated plot, so I'll break it down. What I'm showing here is kind of the landscape of pulsation modes in a star as it crosses the HR diagram from left to right, from O and B type star across to become a red supergiant. And the takeaway here is that very few to no modes are actually excited in these stars. However, after a star loses its envelope, it turns out that things get a little bit more complicated. The landscape of possible modes gets a lot more complicated, and a lot more of them can be excited. What's actually going on here is that there's a ratio of timescales in these stars, the thermal to dynamical timescale. The dynamical timescale is the timescale that we think, or that pulsations happen on. And by and large, the ratio of these two timescales is very large in most stars. One way of interpreting this is that you kind of reduce this equation down to show that this happens when the luminosity to mass ratio is small. However, if you can make this luminosity to mass ratio very large, for instance, in a Wolf-Rayet star, which has lost most to all of its envelope, but is still very high luminosity, this assumption no longer holds. You actually need to take into account in the pulsation equations the interactions with temperature and luminosity fluctuations. The equations get more complicated, and they allow for a lot more possible solutions. Oh, cool, awesome. All right, I will hustle. They allow for a lot more possible solutions, and we can observe pulsations in them. Wolf-Rayet strange modes are an example of this. And so we decided to go look for pulsating supergiants, just as a way of finding post-red supergiants. So that's what we did in a large sample of yellow and red supergiants with test light curves. And I'm going to show 4 periodograms here. I will quickly note in these top 2, the top one is a red supergiant, the second one is a yellow supergiant. Both of them show this rising power at low frequencies, which looks a lot like that stochastic low frequency variability. We find that stochastic low frequency variability is ubiquitous, not just in O and B type stars, but across the entire upper HR diagram. We characterize the stochastic low frequency variability by fitting them with this function to derive characteristic timescales. We can do things like plotting them as a function of effective temperature. Whether or not there's an actual trend going on here in this plot, a reasonable question you might ask is, hey, aren't yellow supergiants just like really big sun-like stars? Isn't this just like granulation blown up? If it was, then the points would go up and to the right in this plot, but they don't. So whatever the stochastic variability is in these stars, whether or not it's the same as what we're observing in O and B type stars, it's not just blown up granulation. On top of these bottom 2 periodograms, you'll see superimposed on top of the stochastic low frequency variability are peaks in the periodograms. So if I take out the kind of rising power at low frequencies trend, I divide that out and I plot the resulting periodograms in the HR diagram, I get this. There's a little bit, or there's a few cool things going on that I want to highlight. One is over here on the left, these alpha Cygni variables. This is a known class of pulsating massive star. It's actually a really funny one historically. Lots of different kinds of variable massive stars have just been like lumped in with the alpha Cygni, so it's a bit of a mess of a class. Up here in green is an entirely new class of variable massive star. Their periods of variability are far too short to be rotation or binary interactions. And so we're left with pulsations as the last possible origin of this variability. These haven't been discovered before, so we called them fast yellow pulsating supergiants, or FIPS for short. Yes, I know grammatically it should be fast pulsating yellow supergiants, but FIPPIes just doesn't roll off the tongue. And so a couple years later, we decided to come back, try to find more of these FIPS and characterize them in a much larger sample of stars with more test data and a new method of disentangling the stochastic variability from the coherent variability or periodic variability. Now we can actually characterize where in the HR diagram these FIPS live. They all live above a log luminosity of 5, which is really interesting. Their tendency, or rather the fact that they're all found above a log luminosity of 5 is a statistically significant thing. So no contamination in test pixels is an issue. We identified a number of contaminating periods in this sample, but it's the fact that these are all found above a log luminosity of 5 is statistically significant. Not only that, but if I compare the location of FIPS in the HR diagram, that's what I'm showing here in green, to the location in the HR diagram of type 2p supernovae, that's what I'm showing here in red, we can see that, like I mentioned earlier, their luminosities cut off at a log luminosity of about 5. At the same time, the progenitors of type 2b supernovae, these are partially stripped supernovae that in the 5 of them, I think that we've had directly imaged progenitors of, they're all yellow supergiants. The distribution of those progenitors in the HR diagram I'm showing in the purple and blue points. I'm cheating, it's actually just 5 objects, but taken from 2 different papers. And so they have slightly different positions in the HR diagram. In any case, we find that the positions of these stars at a log luminosity of 5, where they take over from the type 2b progenitors, especially in combination with the location of FIPS, paints a really interesting picture. So the picture that we present is this. So in our kind of evolutionary scenario that we present, red supergiants above a log luminosity of about 5 experience some kind of strong mass loss. Maybe it's winds, maybe it's binary interactions, maybe it's outbursts, maybe there's a whole bunch of Betelgeuse great dimmings out there that we're just not capturing. So I think that's actually unlikely. This serves to decrease the lifetime of the red supergiant phase above this log luminosity, which we can now see in populations of red supergiants. These stars then evolve bluewards in the HR diagram as post-red supergiants, where they may pulsate as FIPS, causing an increase in the relative numbers of yellow supergiants up here. Then they undergo core collapse, and they maybe are observable as type 2b supernovae. That's kind of the picture that we paint here. Like I mentioned, there is some issue with contamination in the test pixels. And so we have been going back and doing a careful job going after our samples of yellow supergiants from the ground, getting some follow-up. The first result from this follow-up was just published in the research notes of the AAS by my student, Caitlin Chen, who did an awesome job. She found that FIPS are statistically significantly more likely to have H alpha emission than the general population of yellow supergiants, which is pretty neat. The next step of this is to actually look at spectroscopic variability in our sample. This is work in progress, so please don't share, but we are indeed finding that in our data, which is pretty exciting. All right, so final takeaways here. We're in this really exciting time, like I mentioned. We have these really exciting space-based missions that are giving us oodles of data, which means that we can start to do machine learning with them, provided that we are doing a careful job with our machine learning, right? A commonly used phrase in machine learning is garbage in, garbage out. We need to actually trust our features and trust our labels. We should not just be applying machine learning blindly. So there is still a lot of really there's still a lot of use for precision studies done from the ground, star by star. I know I'm at Carnegie, which means I and y'all as well have lots of cool access to Magellan. And so there is room for surveys from telescopes like Magellan. Let's see. In addition to the space-based missions that I mentioned above, we also have TESS, which is revealing lots of undiscovered phenomena in massive stars, evolved and unevolved, including the fast yellow pulsating supergiants and stochastic low frequency variability. And finally, if I have to leave y'all with one thing that I want theorists to be thinking about, it is that the place to look for exciting new massive star science is at a log luminosity of 5. I know that's like a really specific thing, but it is at that luminosity that we see the red supergiant problem show up. It's where we see the transition from supernovae 2p to 2b's. It's where there's a kink in the observed mass loss rates of red supergiants. I think this is a really interesting place for us to look observationally and theoretically. And so everyone, regardless of whether or not you work on massive stars, drop what you're doing and look here in the HR diagram. Okay, that's it. I'll take questions.